Drivers of both boats and cars and operators of machinery all feel that there is one big risk when dealing with metals. This is rust or corrosion of the metal. Corrosion is the breaking down of the metal. In this lab, we wanted to see how fast certain metals corrode. We used H2SO4, sulfuric acid, because it is a very common acid that is used in almost 99% of all household products. So why would we still use this acid? The reason we chose this was because due to surface runoff, these acids usually wind up in lakes or even on the roads, so it will be in direct contact with the cars, boats, or machinery operating. The reaction that takes place is an exothermic reaction, and in this case, a single replacement reaction. This replacement is between a metal and hydrogen in the H2SO4. The choice of metals is a very important one. The reason we chose the metals we did, which was zinc, iron, and calcium, was that not only were all of these reactive metals, they were also in the same period. This makes it so patterns can be seen within the sublevels and can be related to atomic trends. Mole conversions were needed next to figure out how much of each of the reactants were used. After the experiment was done, a conversion was done to find the volume of the balloon and to next find the percent yield on how much was calculated and how much hydrogen gas was supposed to be created. The main purpose of this lab was to find out which of the metals was the least corrosive when put in H2SO4. It was expected that the metals that were placed higher on the activity series would corrode the most, as they are more reactive. In this lab, the independent variable was the time intervals used for each trial. The dependent variable was the amount of hydrogen gas released, in this case by determining the circumference of the inflated balloon. In this lab, we used 9 Erlenmeyer flasks. We did 3 trials with iron, zinc, and calcium, giving us 3 Erlenmeyer flasks for each metal. We measured out 1.5 grams of powdered zinc for each trial. We also measured out 1.5 grams of calcium pellets for each trial. We also measured out 1.5 grams of powdered iron for each trial. And we also had a container of 6 molarities of sulfuric acid, string, and 3 stopwatches. Next, we measured the halfway point of the balloon with a marker so we knew exactly where to measure the balloon from when it inflated. Then we had to measure out 6 molarities of sulfuric acid, pour it in a beaker first, and then pour it in a graduated cylinder to be safe. We poured 40 milliliters of sulfuric acid in the graduated cylinder and poured 40 millimeters of sulfuric acid in each beaker.
Next, we massed out 1.5 grams of each of the metals, zinc, iron, and calcium. We tried to get the sig figs as close to 1.5 as possible. We did not have enough 6 molar H2SO4, so we had to do a dilution experiment with 9 molar H2SO4.
We started our first trial by pouring calcium pellets into the sulfuric acid in the small Erlenmeyer flask. However, after trying it for all 3 trials, the calcium balloon did not seem to blow up. This was probably due to the size of the pellets.
Powder is better in reactions because the H2SO4 has more surface area to react with the metal powder.
Next, we poured iron powder into the flask and waited for the balloon to inflate.
At this point, we swirled the flasks, especially iron and zinc, because we wanted to make sure the H2SO4 was touching all parts of the metal.
Next, we poured zinc powder into a separate flask, then put the balloon on top for it to inflate. We also shook the flask to make sure that the H2SO4 was touching the zinc. We then did 2 other trials.
Throughout the whole experiment, we saw that iron had the biggest balloon in circumference. This held true to our calculations, although calcium should have produced the most moles of H2 gas. Iron was the second most moles of H2 gas, and the reason why calcium didn't react was because it was put in pellets, and iron released 2.7 times 10 to the negative second moles of H2 gas, and zinc released 1.15 times 10 to the negative second moles of H2 gas. So that's why the zinc balloon was just a bit smaller than the iron balloon in the end. If calcium were in powder and we changed the experiment, we calculated that there would be 3.7 times 10 to the negative second moles of H2 produced, which would be the most amount of moles, so the balloon would be the biggest for the calcium test.
We first set our intervals at 30 seconds, 60 seconds, and 90 seconds. However, we found out that the balloon didn't inflate as fast as we thought it would be. So we changed our times to 2 minutes, 4 minutes, 6 minutes, 8 minutes, and 8 minutes. We also wanted to find the long run of the balloon, so we also calculated the balloon at 30 minutes. The way we calculated the balloon was by placing a string around the balloon to measure the circumference of it. As you can see, iron and zinc inflated the balloon after we put the metal into the acid. When we put the metal into the acid, the fluid turned opaque and was a gray-white color. Zinc floated on top of the acid, while iron was more evenly distributed throughout the acid. From this experiment, it was determined which car metals were more corrosive. We learned that powdered iron corroded the most out of the three metals when added to H2SO4, followed by powdered zinc, and finally calcium pellets. It could be then concluded that based solely on our experiment, calcium produced no reaction. Therefore, according to our results, calcium pellets should be used to construct cars. However, calcium reacts violently with water. Therefore, theoretically, zinc would be the best metal to make cars out of.